Okay, so in the last class, what we have seen that okay, in this minimum card, we are having greater equals to 2% chance that this Kargar's min cut algorithm, if we run a single time, okay, if we run that algorithm, then it will be having 2% more than 2% chance. Maybe it might be 50%, but the lower bound is 2%. It may also be 2% that we will be getting the correct result. Okay, that whether the min card surviving or not, all the edges of the min card. Now we argued that okay, we can improve upon that. Okay, right. So how this improvement is done? So how can we do this? That is the fundamental question that was answered in that Kargar's min cut, and that is being utilized in an ad hoc manner in several different randomized algorithms. Okay, so what is the main idea behind that? The idea is roughly that the repetition ensures fault tolerance. Repetition. We have to run Kargar's min cut algorithm multiple times. Okay. We have to run a randomized algorithm multiple times. If I am at the first iteration, if maybe we are having this kind of bizarre result, 2%, then we have to repeat our algorithms. Okay, and each of the algorithm will be producing some answer, some min cut. Okay, it may be min cut, it may not be, right? So it may be in some cut we might be getting B and D. In some algorithm, whenever I am running that algorithm next time, I might be getting A, C, D. Okay, so this is clearly not the min cut, but this is the min cut. Okay, so the thing is that if we repeat multiple times, then in one of the repetitions, then definitely we might be getting the min cut. Okay, right? Are you with me? Okay, so the idea is that repetition ensures fault tolerance, right? So here, uh, one real life advice that we get every time, or we do unknowingly, that okay, making two backups of your hard drive is related to the fact that the probability of failing is much smaller than one does. Okay, so your desktop or laptop will be having one hard drive and you are having one external hard drive. Okay, why you are keeping this? You are keeping this in mind that it may be the case that okay, the laptop hard drive or the desktop hard drive might be crashing. Okay, at that time you can recover your data. So if that crashing, if your laptop hard drive crashing with probability half, that is 50%, and then your external hard drive also having probability of crashing is half. Okay, then at a time simultaneously both will be crashing. What is the probability of that? We have to multiply. These two are independent event. Okay, so the intersection of this guy and then this guy will be, as we know that whenever we are having independence, we have to multiply the probabilities. So it will be 1/4. That is 25% chance that both will be simultaneously be faulty at the same time. Okay, so your data will be surviving is much more, right? And if you are having multiple hard drives, so you may be thinking that okay, after this class you might be thinking okay, I'll be having 4 hard drives. Okay, so if I'm having 4 hard drives, will the probability of surviving data will be increasing or decreasing? Huh? Increasing. Okay. Okay, so the more I'll be having the repetition, okay, the more I'll be having the repetition. Hmm, hmm. Hmm. What is your roll number? 175. Note it down. Okay. So this repetition we'll be doing as we are dealing with this mean cut algorithm. Okay. So the mean cut algorithm in this, if I relate this analogy with this mean cut algorithm, then we can think of each device. Each device correspond to each run of the mean cut algorithm. Okay. In one run, if probability of error is more, then in two runs we'll be having it less. Okay, right? So probability of getting the error, even if say, so 2% we had the success probability, the failure probability might be 0.98, something like this. Okay, so say if the failure probability is 9, then in two runs the failure probability will be 0.9, that means 0. Almost 8. Okay. So you see, the if I am having two runs, the failure probability of not getting the min cut is decreasing. Okay, right? Are you getting? It's absolutely simple but very intuitive idea that we are applying right now to prune our algorithm to get the correct min cut almost every time. Okay. So now this we can come back to our analysis that we were doing. So probability of getting the min cut in one run, that we have, what we have got, that is greater equals to 2 by n into n minus 1. Okay, that we had in the last class, we had that result we had. Okay, so probability that we'll be getting the min cut in one run, one single run, if I am having, that is greater equals to this. Okay, so probability of not getting the min cut in one run, what will be that? That will be less equal to 1 minus this, 1 minus the success. Okay, isn't it? Are you with me? You? Yes? What is your roll number? Huh? 192. 4. Say, now, now the question is that, okay, how many, as in that case, this hard drive, we have seen that, okay, we are maintaining 2 drives or 4 drives, it's really decreasing the probabilities. In this case, in this min card, the question is how many runs we should be having, how many times we will be running the Kargar's min cut randomized algorithm to get the correct answer. Almost always. Okay, right. So say we run the randomized min cut these many times, n times n minus 1 times this ln n, natural log of n. Okay, ln n, and the output of the min cut out of all iterations, and we are out of all these runs, we are outputting the min cut. Okay, in some cases it might be say b In some cases, it might be AC. In some cases, it might be, say, ACT something. Okay. So in all iterations, we are noting it down out of all iterations. Okay. And then out of all iterations, whichever is the minimum cardinality of this, whichever is the minimum, that will be outputting. Okay. Right. So that is the idea. Out of all this, the cardinality of this maybe we can take one, which is the minimum. So that may be the min cut. Right. Now if you are asking that how did you get this number? These many number of times we have to repeat. How did you get this number? Okay. So the answer lies that we had some kind of back calculation, okay, to get this number. Okay. So you will be getting why we are running it for these many times, because our algebraic expression will be much more simpler in that case. So now what we can say, okay. So the probability that so in our case in the device case, okay, so it was half times half, okay, right. So if I run 2 times, it is half times half. That means what we can say, it is half time square. If it is 3 times, three hard drive we are having, then it is half times half times half. So it is half whole power 3. Okay. So if it is n times n number of hard drives we are having, so it is half whole power n. If I number of hard drives we are having, it is half whole power I, right? Okay. So the failure, the probability that the output is not a min cut whenever we are having these many number of runs. Okay. So in one run we have got that this is less equal to 1 minus 2 by n times n minus 1. Okay. That means it is 1 minus a. So this is our a. Okay. Right. If I am having 2 runs, it will be 1 minus a whole square. If I am having n times n minus 1 ln n number of runs, so it will be 1 minus a whole power that. So that is what it is written over here. Okay. Are you getting? Are you getting? You. Last bench. What is your roll number? Huh? Why the headphone is on? Headphone? What? You are listening music or what? Are you having problem with your ear? Having problem with your ear? Then why the headphone is on? Huh? Sorry. Are you getting what I have said? What I have said? Why this is n times n minus 1 ln n? What is this? Time complexity. Come here. দেখ এখানে এসে মিউজিক শুনছি Your roll number is 123. Note it down. 123. Okay. Now what we are in many of the analysis. Okay. You come here. In many of the algorithmic analysis, we use a formula. We use one approximation that the approximation is 1 minus if it is 1 minus x, it is less equal to e power minus x. This formula is at the heart of many analysis of algorithmic result that we get. Okay, right? So you see here also we have got this form 1 minus x form. So this is 1 minus a form. A is this. So this 1 minus 2 by n times n minus 1, 2 by n minus 1, n times n minus 1, that is x. Okay. So this is of this form 1 minus x. That we can approximate by e power minus x. Okay. Right. So if I am doing that, then what I am getting? So e power, that is this 2 by n times n minus 1. So that means minus 2 by n times n minus 1. Okay. Right. Whole power this. Okay. So a power m whole power n, that is equal to a power m times n. So this formula is at the heart. So that's why it was hammered in your 7th or 8th standard. Okay. So that is whole power this, whole power this. That means it should be multiplied with this. Are you getting? Huh? Now you see this n times n minus 1 and this n times n minus 1 will be cancelled out. So why this n times n minus 1 ln n times we are repeating? Because we have seen that we have here this term having n times n minus 1. To cancel out this, and we know that this is of the form 1 minus x form, and we will be approximating by that inequality e power minus x. So that back calculation we had in our mind, and then if I am having it e power minus x, and then I am having whole power n times n minus 1 ln n. So n times n minus 1, if this n times n minus 1, which is denominator, that should be cancelled out, then we have to have that. Okay. N times n minus 1. Right. So, and then after that, E is there. So some ln n might be there. Okay. So that's why this, if I exchange the C and N, then you will be omitted after that with that ln ne formula, and then we'll be having a nice expression left. Okay. So this was the back calculation we had in our mind, and then we are telling, okay, if I am repeating n times n minus 1 ln n, then definitely something going to happen. Okay. So what is happening? So you see this this thing getting cancelled out. So which is left? E power minus 2 ln n. Okay. So minus 2 that I am taking here in this n power. Okay. That we can do. So it is n power minus 2, and then n power minus 2 and d is exchanged. So e power ln n minus 2. So from here I can write this. And then this n power minus 2, and then this e is exchanged with that formula we know. Every now and then logarithm comes, and then this formula rescues us. Okay. So then ln n e, that will be 1, so it will be left with n power minus 2. That is 1 by n square. Okay. So this probability is less equal to not getting a min card if I run this many times. So if I run this many times, what will be the probability that I'll be surely getting? So 1 minus 1 by n square greater equals to this is. So if it is less equal to, then that will be greater equals to. Okay. So with this probability, 1 minus 1 by n square, if I run this many times with this much greater equals to this much probability, we will surely be getting the min card. Okay. So if I put n equals to 10, then it will be almost greater equals to this 0.99. Okay. Right. So that means 99% or more chance that we will be getting the min card in a randomized algorithm if we run it this many number of times. Okay. This many number of times, and then I am taking the minimum out of that. Okay. Right. So this is the analysis is so beautiful. That means everything is crystal clear. Okay. Why we are getting this more than 99% chance we are having that Kargar's min cut will return the min cut exactly we are desiring. Okay. So this is all about these randomized algorithms, what we had to discuss. Now we can go to this graph algorithms. Okay. Graph algorithms. And this is from this few slides are from the combination of this Robert Sedgwick. His book I have referred, Algorithms. This book is very good. Okay. Lots of good, compact implementation in terms of Java is given in this book, Algorithm, Java, C++, I guess. So this book, and the thing is that it is having every algorithms comes with its applications. What are the major applications that we are having? Say we are learning BFS, breadth first search, right? So what are the possible applications that so far we have applied breadth first search? So in that book it is documented, and in this book, and also Sedgwick follows that KT book, Kleinberg Tardos, where the applications are also mentioned, and especially the companion lecture slides of KT book that they follow. They follow Sedgwick and his colleague. Okay, so Kevin Wen. So they follow those lecture notes. Okay, you can go through that also. But this guy, this Robert Sedgwick, having videos also, you can check. And this book is very good, Algorithms. He is from Princeton University. So here what we are dealing with is graphs. Okay. This data structure is so important in computer science because many of the classical, modern day, also all applications we can transform into graph domain and we try to solve. Okay. So this including the Google Map, the Facebook recommendation, all these things we are transforming this into graphs and we are solving it. Okay. Right. And that's min cut algorithm we have seen. It's a graph problem that just now we have seen. It's a graph problem. We are having several nodes and they are interconnected with each other, maybe something like this. Okay. How that interconnection is coming, that depends on application to application. Okay. So why we should be studying this graph? And this is written as undirected graph. So the graphs might be having two types. Say some direction might be there also, right? Or direction may not be there also. So first we study this undirected graph. Many of the results that we are having this undirected graph is true for directed graph also. So as I have told you that okay, this why we should be studying graph algorithm, because it's plenty of at the first place we are having plenty of applications. Okay. Plenty. It is plaguing the computer science field, the graphs. Okay. Say this border graph of 48 contiguous United States. Okay. How the border areas they are connected directly. Okay. We are having paths from here to here directly we can go. Okay. So this problem, okay, can be formulated as a graph problem. So this is protein-protein interaction network. Okay, lots of work going on in this field. It's now graph machine learning is coming into picture. Okay, so we are having proteins. How so each age. So these are say proteins, and each age is the interconnection between them. Okay, how they are interacting with each other. We are taking the information of that and we are transforming it into a graph. And then there are lots of application if I am discovering the structure of this protein-protein interaction, then maybe that could be utilized in drug discoveries. Okay. So this is a graph that we have to study and we have to infer so many things. And the machine learning is coming into picture here. It is no longer restricted in classical graph algorithms. So this is map of science click streams. That means the nodes are some computer scientist web pages. Okay, and say some say Sedgwick is searching from his website to other website. Okay, so all these are how say Sedgwick is searching from his website to which websites. Okay, so that is connected here. Okay, that information is captured here. Okay, how I am clicking as a computer scientist, I am surfing the pages. Okay, that can be taken in the form of graph, and we can analyze the pattern of any scientist. Okay, working in our domain. So this is 10 million Facebook friends. This is a gigantic network the Facebook is having. Okay, and they study this. So it's a natural idea to study Facebook interconnection network as a graph problem. Okay. Hello. হ্যাঁ ক্লাসে এই 12টা 12:30টায় ফ্রি হবে আবার একটা থেকে ক্লাস কিছু বলছিলে তাহলে 12:30টায় যাবে Okay, so this Facebook network, we will be seeing a small prototype of the Facebook network, how Facebook is recommending friends. Okay, so using BFS, maybe they are recommending friends. So you are Facebook, every time you opening up your Facebook account, Facebook recommending some friends. Okay, friends request to you, right? How at a fundamental level, what they are doing, maybe they are utilizing the breadth first search technique. Okay. So this FCC lobbying coalitions, who is having coalition with whom? So this is the FCC of USA, this organization. Okay, and who is lobbying with others to influence this? Okay, so this also can be thought of as a graph. Okay, who is which guy is having connection with whom? Okay, so that or who is going to influence whom? Okay, so that the FCC will be ultimately be influenced. So that thing we can take into account here, and we can analyze that this network. There are lots of analysis. In lots of ways we can analyze graphs. We'll be seeing what are the ways here. Okay, some of the ways which are very commonly studied, that we'll be seeing here. So this is Framingham heart study. That means how these hearts of persons related to the obesity of the person. Okay, right. So that may be represented as this graph, and we can study this. Right. So this is internet as a big network. Okay. So that means say this is NIT Durgapur. So this NIT Durgapur is connected to the whole world. How? Okay. Right. So maybe this is Stanford. Okay. Their internal network, and then they are connected with the others outer world. Maybe. Okay. So this way we can have a gigantic network. This internet could be thought of as a graph problem. Okay, and we can study a lot. So this is you see we are having graphs, having many applications. This is communication network, the circuit. We can study mechanical. So vertex are the joints, and the edges are the rods, beams we are having. Okay, a bridge, we are having many joints, and then we are having rods connected to it. So a bridge can be, first of all, as whenever we are trying to build up one bridge, then how many such joints we'll be having, and then which joints will be connected with which rods, and then say this joint may be connected with this with a rod, and then this will be connected with this. These edges might be representing some rods, beams, etc. Okay, springs, right? So all these way we can think of, say, this board game, this chess can also be thought of as a graph problem. The board positions will be the vertex, and the legal moves will be the edges. Okay. So lots of this protein network we have seen. Okay. The proteins are the vertex, and the interactions are the edges, right? So molecules, chemistry, we are having chemistry can be thought of as a graph problem. The atoms are the vertices, and these bonds are the edges. Okay. So lots of ways we can think of that problem is a graph problem, and we can solve this. Okay, this problem in many ways. We can ask several different questions on a general graph, and if we are in this, we are trying to motivate that we need to study graphs. Okay, we are having lots of applications. Now what we'll be trying to do is we'll be abstracting that problem as some nodes, we are having, and then we are having interconnection between these nodes. Okay, if I am abstracting like this way, I can cover up all these applications. Okay, all these applications, right? So we have to study the graph problem as a node versus node and edges. Okay, nodes are there, there will be interconnection between the nodes, and this idea having plenty of applications that we have seen here. Okay, now from now onwards, what we'll be doing is we'll be telling that the graph G will no longer be telling that it is a traffic network, or it's a communication network, or it's a protein-protein interaction network, or whatever. We'll be telling that the graph G consisting of vertices and edges. Okay, we'll be abstracting those viewpoints here with these mathematical symbols. Okay, are you with me, everybody? Right. Okay. 20 minutes. Huh. So now this, whenever we are having some edges, some nodes and edges. Okay, then we can ask, say these 5 nodes is also could be thought of as a graph. Okay, and this node may be a madman. Okay, he or she is not having any kind of friends. Okay, right. So he or she is in isolation. Okay, or maybe a genius guy. Okay, like Paul Gauguin. Have you heard about this guy? He he had self he took self exile in some island. Okay, and he was a world famous painter. Okay, so maybe that guy is uh, is represented here also. He is a human being. Okay, also. So this is a graph also. It is not the case that this guy should be having a connection with others. It may be one isolated one also. So now this ST path, this question we can ask. Say if this is a graph, then whether this guy having a path to this guy. Okay, right. So we are seeing that okay, this guy having a path because via this we are having a path from this to this. Okay. But whether this guy having any path with this, the answer is no. Okay. Right. And what we do is say this network we are having some edge weights. Say maybe this 10, this edge having weights 10, this edge having weights say 5, 6, 4, something like this. Okay. Right. So this may be thought of as the city is having distances. So these two cities having distance 10, these two cities having distance 5, and so on. Now if I ask that, okay, what is this is our S and say this is our T, what is the shortest path from S to T? So we are having maybe two paths from S to T. One is going in this direction and another is going in this direction. Now if I add up the h cost, then I am getting it is 10 plus 5, this is 15, but it is in this path, it is 4 plus 6. So 10. So this is the question. This is absolutely a viable question. Okay. So whenever this Uber is recommending some kind of cars to you, how they are recommending you? They are more or less they are applying these shortest path algorithms. Okay. Who are the guys who are there in your vicinity, right? And those guys will be recommended to you mostly. Okay. So maybe they might be thinking that this guy is the first one. If he denies, then out of that I'm extracting that node out, and then I'm recalculating the shortest path. And this guy, the next shortest path will be this. So this is the next one. Or in his or her presence, that driver, we can compute 2 or 3 shortest paths. Okay. So that we can have some backup mechanisms, right? So this is shortest path is having, I think, most of say the revenue that whole world is generating through internet right now, and maybe say half of the revenue being generated through internet throughout the world. And the algorithm which is at the very fundamental level of generating that revenue is the shortest path. Okay. Every communication network, every routing table, okay, they are applying the variant of the shortest path of the other. Okay. So whenever you are trying to search something, that will be going through some router in our NIT Durgapur. Okay. So how this routing table is taking care of that, how to uh, di- how to uh, how to channelize your request throughout the world. Okay. So the router is continuously keeping track what is the shortest path. Okay. Right. Okay. So the next question that is also very important is that cycle formation. Okay. So is there a cycle in the graph, right? So maybe this graph having a cycle. Okay. This graph having a cycle, and you see, say if this is the graph, say directed graph. Okay. So now you see, if I start from here, if I go like this, and then if I come like this, and then if I come like this, and then if I come like this, then I'm coming back to the source node where I left. So this is forming a cycle, right? And this graph, this is a bipartite graph, and this is having plenty of applications. Okay. Plenty of applications. So we study kidney exchange problem with this. So cycle, whether a graph is forming a cycle, is having plenty of applications. Okay, plenty. Okay, I guess it's done. Okay, so today up to this, and maybe I don't know whether there will be holidays in the next week, some classes. But if it is holiday, I'll be taking the class online because we have to cover up lots of things.